Hi, I have built a homegrown surveillance system based on the Internet of Things on the Raspberry Pi platform to monitor the environs of my home and detect potential intrusions. This is an Internet of Things IoT implementation where multiple surveillance units, each of which is a Raspberry Pi 3 with a camera, send images to a central server wirelessly using the MQTT protocol. The server, or more appropriately, broker, then aggregates these images using Node-RED and displays in a nice image gallery with other annotation like alerts. In other videos, I have shown how to detect motion with image analysis and even detect objects and people, even detect objects including animals and people using deep learning on Raspberry Pi. Here, I will show you how to build an Internet of Things, how to engineer this system on the Raspberry Pi platform with open source software. We will learn about Docker and the Internet of Things IoT stack of software with all the ingredients we need to exchange messages among devices that are interconnected with each other, to aggregate information and apply rules of our making, to store time series data in a telemetry database, and to create interesting dashboards with compelling visualizations in the presentation layer. All this and more on a Raspberry Pi costing less than $50 and with free and open source software. Stay tuned. We will start by installing Docker and Docker Compose on the Raspberry Pi. Next, we will install the IoT stack, the Internet of Things stack, which is all the tools that we need to build with. And we will do this installation with Docker. In this step, we'll dive deeper into Docker and learn by utilizing Docker to install our IoT stack. Then we will install Node-RED on the Raspberry Pi 4, the Pi that we will use as a server. I will show you how to use MQTT to integrate multiple devices, microprocessors, through a series of demonstrations, through a series of live demonstrations. And with this know-how about MQTT, I will then show you how to write a Python script to automate sending images from a surveillance unit, a Raspberry Pi with a camera, to the Raspberry Pi 4, a broker, to the broker, the Raspberry Pi 4, which acts as the centralized server. And so in step number 1, in part 1, we'll install Docker and Docker Compose. So you can follow the instructions in the guide, and I will walk you through these instructions and what they are. The first step, we call it step number 0, is always to update the system with the sudo apt-get update and sudo apt-get upgrade. In step number 1, use curl to get the installer from docker.com and then execute it, pipe it to the shell. After step 1, Docker is installed on the Raspberry Pi and available to use to the root user. And we typically don't log into the Raspberry Pi as root. We log in as some other user, typically the user Pi. And so to enable the non-root user to run Docker, add the user pi to the user group Docker. Alternatively, add the currently logged in user to the user group Docker. So at the end of step 2, Docker is installed and accessible to the currently logged in user. So now let's install Docker Compose. So Docker Compose is installed using the pip3 installer of Python 3. So in step 3, satisfy the prerequisites, which include installing Python 3 and the pip3 installer. If you have Python 3 already installed on your Raspberry Pi with pip3, then these last 2 lines of step number 3 may not be necessary. However, you can go ahead and execute all these 3 commands at the terminal prompt anyway. Now, armed with pip3, use pip3 to install Docker Compose. So at the end of step 4, we have Docker as well as Docker Compose installed and ready to use. And the last step, step number 5, we would want Docker to start when the Pi boots up. So use systemd to enable that, enable Docker to start each time the Pi boots up. So that is the installation process for Docker. So here are the steps again to install Docker: update the system, get and install Docker from docker.com, add the user Pi to the user group so the non-root user can run Docker, install Docker Compose prerequisites. Docker Compose is installed using the pip3 installer of Python. Then with pip3 install Docker Compose, and then use systemd to set up Docker to start each time the Pi boots up. So why Docker? So why do we need Docker? So the answer lies in the web of dependencies. And as the entry point into this, let's consider a deep learning application in Python or R. Have you wondered how a deep learning application, such a complex piece of technology, fits in a screen full of Python or R code? Just less than a page of code. And the answer lies at the top of the script, where we see the packages in Python or the libraries as they are called in R that the developer has imported into their own code. And where do these packages or libraries, where do these modules come from? Well, they come from the community of contributors in the open source community who make available their code for others to use, right? So when we import these fruits of open source collaboration into our own code, we end up writing very compact code to achieve quite sophisticated tasks like deep learning. So the contributors giving away their code and building on each other's work makes for fantastic speed of development in the open source world. In fact, the trend in community contributions is often the most compelling reason that drives a data scientist's preference in programming languages. And while this is fantastic and solves one problem of accelerating research and development, it creates another problem because modules are always evolving. And in this web of dependencies, incompatibilities may arise. So this is not usually a problem in an active community where contributors are actively contributing code and developers are actively consuming code, as gaps quickly come to light and can be resolved in a reasonably short time. In fact, this is why, as developers, it is a good idea to set aside time in a planful way to refactor code from time to time and keep all the dependencies up to date, sync them up with the latest versions. To avoid gaps building up and the house of cards coming crashing down later, like we see these cards crashing down on Woody. So occasionally it may happen that one of the modules in this web of dependencies is slow to keep up with the changes, and it becomes a point of failure. For example, to give an example of this situation, version 3 of Python introduced the print function to replace the print statement in earlier versions. Now, the print feature is ubiquitous in code. Can you imagine code without the print feature? So from version 3 onwards, a single print statement lingering in a module that hadn't been updated to use the print function instead of the print statement could bring the whole house crashing down like the pack of cards, as we just saw, as we just described. So what is the solution? Could we perhaps freeze a snapshot of the dependency tree in time and put it into a container for use in isolation, with all the isolation from all the changes? So in Python, we have this concept of virtual environment for this purpose. In a virtual environment, we put all the required modules, all the modules that an app requires, in a self-contained container, a folder, to make available to the Python interpreter. The modules are listed in a requirements manifest, and the version and that manifest has the version number. Now, the way in which the Python interpreter accesses modules is also modified in a virtual environment to provide isolation. So the interpreter will not look for the modules anywhere else but this environment. So this guarantees that we have an environment that is reasonably well isolated from changes and potential disruption arising out of these changes as these modules evolve. So this is a type of containerization, but this will only work for the branch of the tree of dependencies that is Python. Now the root of the dependency tree go down all the way to the operating system. So how to deal with this? And the answer to that is Docker. And we'll see about this as we install our Internet of Things stack, our IoT stack using Docker. So in the software world, we talk about full stack development, which means development with all the tools that we need to build with. And so when we are building with Internet of Things, here's an IoT stack that is very, very popular because it is open source and free, and also has all that we need to build an IoT application. And this stack has 4 components. The Mosquito MQTT software. What does this do? This implements the pub-sub model of persistence. So in this model, information is organized by topics on a central hub called a broker. And a publisher publishes messages to a topic. And the moment the publisher does that, any subscriber to that topic gets notified that that topic has been updated. The beauty of this model is a topic on the broker can have any number of publishers and subscribers, making for a very fluid model of communication. These publishers and subscribers are other computers elsewhere. Then Node-RED. Node-RED implements ETL, which is the acronym for extract, transform, and load. Extract data, for example, as a subscriber to a topic on an MQTT broker. Transform it by applying the business logic of our application. This step of applying the business logic typically bakes raw data into usable, interpretable information. And then once we have the information, load it into reports for presentation. Then InfluxDB. So although the MQTT broker receives and then broadcasts messages, receiving messages from publishers and broadcasting them to subscribers, it persists data for a small amount of time, 7 days, 15 days. Once the data are baked into interpretable information, we want to save that information into a database. The typical IoT application works with time series data as time series arising out of time series signals. InfluxDB is a telemetry database where we can store these time series signals for longer, potentially forever. That is the life cycle of the app. The MQTT broker's job is just to pass messages on. So this is the place where information is persisted. We could use a vanilla relational database, a vanilla RDBMS. So why use a telemetry database? Well, that's because the telemetry database is geared up for CRUD operations. CRUD stands for create, retrieve, update, and delete, and administration of time series data. So all the additional overhead we would incur for handling time series data, time series signals with a vanilla RDBMS, much of that overhead is taken care of by a telemetry database that is geared up for precisely time series signals, data of a time series nature. And finally, we have Grafana for the presentation layer. So on the Pi, we will install this stack on the Raspbian OS, which is a variation of the Debian flavor of Linux. So to simplify this IoT stack further in layman's terms, the MQTT broker is the clearinghouse where messages are received and dispatched between parties that need not even be aware of each other. Node-RED is the home of the business logic. Business logic needs a home. The rules that we apply to bake raw data into information, interpretable information, that is business logic. That needs a home. Node-RED is that home. Once we have information, we want to persist it. And this is information of that has by nature is time series signals. So where does that information live? InfluxDB is that apartment where this information lives forever. And then Grafana is the window into this apartment, and that shows only what matters and dresses it up so it's easy to understand. It's easy to visualize and follow. Now we could install each of these components and any others that we may require on the Pi, just like any other software that we install on the Pi. But then we would be walking into this trap of the web of dependencies. So instead, we shall install each component in a Docker container and then network these containers for use in our app, our surveillance app. So to give a taste of this side effect of the web of dependencies, I'll circle back to where we installed Docker and Docker Compose and use Docker Compose to install a sample app called speed test. So what this app does is once installed on our machine, it it measures and reports the speed of the internet link. So let's do that. So here is the speed test, the Docker Compose file for the speed test app. It's a small file and it is included in the GitHub repo where I have the Jupyter notebook. And we need not get into the weeds of the contents of this file. What is important is that this speed test app uses two components, InfluxDB and Grafana. So two of these components from the four components that we looked at in the IoT stack. And the way to install this app with Docker Compose is execute the Docker Compose up command at a terminal prompt in the folder that has this file. And Docker will take care of the rest. So let's do that. So I've downloaded this file into a folder called IoT stack _ prep. And that's the only file that this folder has, this docker-compose.yaml. And let's quickly look into this file with Nano. So this is the same file that I showed earlier on the author's website. And it uses InfluxDB and Grafana. Okay. And what I'm going to do is run Docker Compose up, the command. And it fails with the error message. No matching manifest for Linux ARM v7 in the manifest list entries. So this latest version of InfluxDB, which it tried to pull and install, that failed. Install in a container, that failed because of incompatibility with the Raspberry Pi, the ARM architecture of the Raspberry Pi's microprocessor. So this is the type of issue that we run into that is related to version control. Because now if I go into the Docker Compose file and roll back to an earlier version of InfluxDB, specifically version 1.8, then it will install properly and I will be able to install this app and run a speed test. So let's try that. Nano Docker Compose YAML. So all I'm doing is going into this file and editing it, and where it says image InfluxDB latest, and we'll come to what is an image and what is a container and how a container is created from an image in just a minute. But all I'm doing is I'm changing this instruction here to tell it to fetch version 1.8 of InfluxDB and use that as it goes about its business. So let me save this Control O and Control X. And now when I run Docker Compose up, which is the command we run in the folder that has the Docker Compose YAML file, now it will spin up the application and run it. So here it is, pulling the images, whipping up the containers, and it's done. And the app is running. Now, I'm not going to go into the details of this app any more than I have so far. All I wanted to illustrate is how simply changing the version of InfluxDB from the latest to an earlier version 1.8 means that our app is running. And without this fix, it would not install, right? It stopped us dead in our tracks. And I've made available this YAML file in case you want to try the exercise that we just did. So it's in the Git repository, IoT stack, where also I have this Jupyter notebook that I'm sharing with you. So go ahead and grab the repository and feel free to run that test on your own. And that brings us back to our IoT stack and installing it with Docker. So hopefully now you see why Docker, to install the components of our IoT stack. And in Docker, so like I'm illustrating with this pop-up book here, this example, the Docker, in the Docker world, we create a container from what is called a Docker image. And a Docker image is just a static file for distribution. So in the world of Docker, fortunately, much of it is very transparent because of text files. Yeah, and the Docker image itself is a flat file, which one can look into to see what is in there. And from the Docker image, we create a container. We spin up containers using the Docker run command. And the Docker run command is a very versatile command. It, of course, requires the image name to spin up the container from. It accepts a variety of optional arguments to configure this container and even to run commands inside it. So once up and running, a container is like a self-contained Linux box running on the host. You can start it, stop it, restart it, remove it, run commands in it. And the beauty of Docker is the Docker engine can spin up as many containers from one image as needed for an app. One of the reasons why Docker is so popular and virtually indispensable in today's world of software development is that this concept of spinning up multiple containers lines up so neatly with the microservices pattern, where instead of building software as a monolith, we break it up into services, both in terms of how we build software and also how we deploy it. And then we orchestrate these services to deliver our app or the user experience to the user. And so as we go about our business with the Internet of Things stack, we will deploy each component in our IoT stack as a service in a container. And to do this, we'll use a script that has been shared by two very experienced makers, Andreas Spice, the self-described guy with the Swiss accent, and GC Garner. So follow the instructions in their field guide. They are simple instructions. What they have done is they have made available a script, which when you download and install, will serve up a menu that you use to select the components of the IoT stack that you want. And this menu is more comprehensive than just the 4 components that we have covered. Now, Mosquito, MQTT, InfluxDB, Grafana, and Node-RED. There is much more that this menu offers should you choose to use it. So once the menu comes up, make your selection, and what happens next is that this little app will create a YAML file to use with Docker Compose based on your inputs. Now, with the YAML file in hand, use Docker Compose up, and magically, Docker will spin up these containers, configure them, network them, and as if by magic, the whole IoT stack is ready and available on our Raspberry Pi to use in building our IoT applications. Yeah, so going back to our Jupyter notebook and summarizing what is in the field guide from Andreas and GC Garner. So they use Docker Compose, which is, as we just saw, the tool from Docker for defining and running multi-container Docker applications. Yeah. So with Docker, plain vanilla Docker, we can also launch containers one at a time. However, it is more elegant when we use Docker Compose and define the containers that we need and how we want them orchestrated together. When we use Docker, we work with a text file. And when we use Docker Compose, also we work with the YAML file, which is a text file. And in both cases, these files contain the instructions that Docker engine recognizes and then executes to spin up containers. Instructions such as what image to use. And as we just saw, an image is a file, which is how we distribute containers in the Docker world. So the container is created from an image. Yeah. So yes, so this approach of Andreas and GC Garner uses Docker Compose, is based on Docker Compose. And the shell script that they make available, which is launched from the terminal prompt, offers a selection menu with many options for an Internet of Things stack, including the 4 that we have described and many more, many others. With the selections from the menu, it then auto-generates a YAML file. As with the speed test example that we saw, this is an ordinary text file with a .yml or YAML extension. These are called YAML files. And think about this YAML file as a recipe for creating containers in the configuration specified for the selected services. That configuration includes the configuration of an individual container and also how they will be networked. And they are also their interface with the host machine's resources like storage, network, etc. We needn't get into the weeds of this because of the work of Andreas Spice and GC Garner. However, feel free to open up the YAML file and interpret it and relate to the instructions in it. It is not difficult. Docker has extensive documentation and also hands-on tutorials on their website, which I have linked to in this Jupyter notebook. So with the YAML file, we are now ready to feed this recipe to the Docker engine using the Docker Compose up command at the terminal prompt, and our containers are magically ready on our Raspberry Pi with a single command. How awesome is that? Note that we use Docker-compose up the first time we spin up these containers, and thereafter we can stop and start with Docker Compose stop and Docker Compose start. So the containers will persist even when they are stopped. If we want to remove the containers, we use Docker Compose down, which then removes them from existence, so they are snuffed out. So let's go and take a look on our Raspberry Pi 4, where the IoT stack is already up and running. So here I am now on the Raspberry Pi 4, I'm using real VNC to open terminals to these Raspberry Pis, which are in my basement in my workshop. And yes, I have real VNC installed on Raspberry Pi, each Raspberry Pi, and I have real VNC installed on my MacBook, where I'm recording this video. And what you see here is the Raspberry Pi 4, and that has Node-RED, Mosquito, Grafana, and InfluxDB. And I have also installed Portainer. I also selected this in the Portainer from the selection menu, from the script made available by Andreas and GC Garner. And this Portainer-CE and Portainer-agent, both are required. What these do is they give a web-based monitoring and management tool for Docker containers. So I can monitor and manage my Docker containers from here. I can start, stop, restart containers all from this dashboard. And I can also see container status and health. So I can see which containers are running and which I have stopped. The speed test container, along with the container that the speed test app uses for Grafana and InfluxDB, those are stopped, right? And these containers, Node-RED, Mosquito, Portainer is what you're seeing right now. Grafana, InfluxDB, these are, so Grafana and InfluxDB are stopped. So to illustrate how to use the Portainer dashboard to start them, I select them and start. And they will soon be up and running. Okay, so both of these have started successfully and are up and running. Now, while it is loading up, yeah, there we go. Note that Portainer is itself running in a Docker container. Yes. So I have 6 Docker containers running. In addition to the 4 that we discussed, there's Portainer-CE and Portainer-agent. And so how do we know that that app is running? Once the Docker container is up and running, how do we access the app? So I will show you how with the Portainer, with the example of Portainer itself. So today, most apps are built as web services, which means that they run in the web browser, like Chromium here running on the Raspberry Pi. So that means the user interacts with the app via the browser, right? And so when we look at an app like Portainer, how do we access it once a Docker container is up and running? Well, in the browser, we type the IP address of the host machine, the machine that is serving the app. So in our case, that is the app is running inside a Docker container on this machine itself. So that IP address is localhost. And then we give it the port on which that service is listening. So the IP address and the port are separated by a colon. And so each one of these services has a port that they will typically listen on. We can configure that service to use a different port. Yes, there is a standard port that is already assigned, and so for Portainer that is 9000. We can see what ports are in use from the Portainer dashboard. Yes, so once we type in localhost 9000 as the URL, then Portainer will load in the browser window. Let's do that. Localhost 9000. Yes. And while it's loading up, similar to this, following this pattern, a Node-RED typically has the port 1880 assigned to it, and Grafana has 3000. So this is taking a while to load. Here it is coming up. Still loading. It is taking up more time than I anticipated. What I wanted to show you was how the Portainer dashboard has rich information about the containers that we are running, including the port assignment, the name of the container, and yes, there it is. Yeah. Yeah. Yes, so from Portainer, one can obtain all this information. Now, notice when you look at the published ports, there are two values which are again separated by a colon, and this is because the port inside the Docker container. So remember, a Docker container is like a self-contained Linux box on the host machine. So it has its own resources, such as ports. And so the port inside the Docker container here is mapped to the port on the host machine. And these information such as this is configuration information, which is supplied via the YAML file. So I just wanted to show you that. Yes, so when making menu selections, add Portainer to the list of services we want installed. So Portainer, to summarize, provides a service monitor that shows container status and health. In addition, it has other features like giving us access to logs, a console to manage services by starting, stopping, restarting, removing. And we have made the command line interface our friend, and let's ease up on that and use visual aids where it is convenient, like Portainer. I'll also point out that for Raspbian Buster, the guide, Andreas and Garner's guide, has a few special instructions. So this is a good time to peek a little under the hood of a Docker, of Docker. And a Docker container uses the kernel of the host operating system. Okay, so what is the kernel? So it is that part of the operating system that interfaces between software applications running on that computer and the computer's hardware. So it is really the meat of the operating system, right? And the Docker container uses the kernel of the host operating system. That is how Docker is perhaps different from other approaches to containerization, such as virtual machines and other operating system components. So there is more to the operating system than just the kernel. And these are part and parcel of the container. In fact, they provide the base layer upon which changes are made. And so whenever a change is made, these changes accrue, they accrue layer by layer upon the base layer. So think about each change as an instruction, given to that Linux box via the command line. And the mechanism for doing that is called a Docker file. So the Docker file will have step by step all the instructions for the command line to change the base layer. So each of those instructions adds a new layer to the image. And this approach of layering changes makes change management easy because it is possible to now peel back layers to any intermediate layer to make changes there, or even branch off in a different direction and add new layers from that intermediate layer. So the authors of this guide, Andreas and Garner, have noticed an issue when the base image is Alpine, which is a version of the Linux operating system. So Alpine provides the other components of the operating system. The Docker container uses the kernel of the host operating system. And the Mosquito image, this session today is about exploring the Mosquito MQTT broker. So this, as it turns out, is based on Alpine. It has the Alpine base layer. So follow the prescribed steps for Raspbian Buster. They are pretty compact instructions. And let me show you where to find them. Here. Now, this is the main page of the field guide. And these are the instructions that I just referred to. Yeah, so it's just a few lines to run at the terminal prompt, and this will address these known issues with the Alpine base image. So that is it. That's our step 2. We have not only installed Docker in step 1, and in step 2, we have also used Docker and Docker Compose to install our IoT stack with the Mosquito MQTT broker, with Node-RED, with InfluxDB, Grafana, and Portainer for managing and monitoring containers on the Pi. In the step number 3, we will install Node-RED on the host Pi. So we have Node-RED running in the container. We'll also install it on the host Pi. And this is so I can do the development work for the surveillance system in an isolated way from production apps I have already running that use Node-RED inside the Docker container. So installing Node-RED is easy. Follow the official Node-RED documentation. It is only 3 steps. First step is to get and install Node-RED. The official documentation already gives the command. Okay. And then scrolling to where we were. Yes. Enable start on boot. Does this ring a bell? Did we not take a similar step vis-a-vis Docker? Yes, so use systemd to start Node-RED when the Pi boots up. And this is if you want to run the Node-RED service in that way. There's one step that I have implemented here, which is to change the default port setting for Node-RED. Okay, so when I go back to my IoT stack on my Pi 4, this Node-RED service, which I'm accessing from the browser, when you look at the URL, you see localhost 1890. And 1880 is the port on which Node-RED runs by default. So port 1880 is already taken up by what? By Node-RED running inside the Docker container. Yeah, you can see that from Portainer. And this also illustrates how useful it is to have Portainer up and running. It is so handy. Yes, so these two services cannot share the same port. So the port is a resource that only one service can listen in on at a time. So the Node-RED installation on the Raspberry Pi, by the way, if you go into the programming menu, you see Node-RED. It used to, Raspberry Pi, it had a Node-RED by default already installed on the Pi with the Raspbian OS. I believe they have stopped doing that now. So in any case, I have installed this myself. with these instructions and set up the port to work off a different port. So I picked 1890. You could pick 1980. You could pick any port that is not in use instead of 1880 here. Okay. And so that is step number 3. And yes, changing the default port setting. So we can specify what port the Node-RED service will use at the time of starting the service when we are doing the startup manually. In that case, we use a -p flag. However, that approach that does not lend itself to automation, right? So to automate this, especially if Node-RED will be starting up every time the Pi boots up, we need to edit a configuration file called settings.js. And where do you find this file? So usually it is running in the home directory on the Pi. Let me show you that. So I will just launch the file explorer, and this might be easier to do from the command line. The command line is our friend, right? Always. So this is my home directory, and here you'll find a directory Node-RED typically. Yes, here it is, cd dot node dash right. Remember the dot at the start. Yes. And now I'm in that directory, and there is a settings.json file there. I'll nano into that file. And in this file, look for UI port. So scrolling, UI port, there it is. Yes, and by default, this will be set to 1880. I have changed it to 1890. Yes, so this line UI port colon process environment port or 1880, change 1880 to 1890. I'm going to exit without changing anything. Yes, so that is how you enable Node-RED to start from. This is how you configure the port that Node-RED will use every time it starts up. Okay. Yes, and now we are all ready for prime time. And what we will do is I will show you how to use MQTT. We have the MQTT service running. Our good friend Portainer is showing us that. And it is running inside the Docker container. Let's find our buddy here, Mosquito, right? So it is running, the service is up and running. It is listening on port. Which port is it listening on? It is listening on port 1883, yes? And I will show you how to use MQTT through a series of demonstrations live. And these demonstrations will increase in complexity, starting with opening an interactive shell to access a Docker container where the Mosquito MQTT broker is running. By the way, Mosquito with 2 T's is the vendor for the MQTT software. So that's the Mosquito MQTT software. And that includes a broker as well as publisher and subscriber, which are called clients. The broker and clients are part of the distribution. So yes, so we will start by using by publishing to the broker from inside the container and also listening to it inside the broker. And from there, we'll step up the complexity until in step number 8, not shown here, I will show you how to automate the process of sending an image from a Raspberry Pi to a second Raspberry Pi hosting the broker inside a Docker container using Python. So in these 7 steps, we will learn all about MQTT. We'll start in step number 1, Inside the container, we will test out the broker by publishing and subscribing with publisher and subscriber, both inside the Docker container. Then we will publish from the host pie, the pie that is hosting the Docker container, to the Docker container, to the broker running inside the Docker container. We will first send a simple text message, then we will send an image, and then we will send a JSON payload containing that image. Okay. So all this will be between the host pie and the broker inside the Docker container. And then we will replace the host pie with a remote pie. So now we have two Raspberry Pis in play. One is a Raspberry Pi 3, cheaper, older version Pi, which is what I'm using for each surveillance unit. And the other is a Raspberry Pi 4, which is hosting the MQTT broker. And just for kicks, I have replaced the Raspberry Pi 4 with the Raspberry Pi 3 here also, just because I am very interested in making this whole Internet of Things work with the cheaper, older versions of Pi that are still readily available. Starting from the Pi 4, the Pi has become more expensive, and I want to make sure that this works even with the older versions of Pi, which may be more affordable and therefore the choice for many applications. Yes, so once we have followed the same steps with the remote Pi, sending text, then image, and then a JSON payload bearing the image, then we will go on and have a look at the Python script that automates this process. So in that Python script, the remote Pi will send a snapshot taken with the Pi camera to the MQTT broker, yes, to the Pi broker every 30 seconds or so, yes. And in the last video in this series, after this one, I will show how that Python script I have adapted to actually make it smarter and detect motion and also detect people and animals and send not just the image, but include in the JSON payload pertinent information like alerts, that can be displayed on the Pi broker alongside the images, with the images in the image gallery. Okay, so we are all primed to do that. Exciting. Yeah, and there are a few commands that I want to make you aware of before we jump into the action. Okay, we'll be jumping into the action in a few minutes. Yes, so let's review all the commands that we'll be using. So first of all, there's only 7 items in my list. We need to launch Portainer. We need to make sure that our Mosquito broker is up and running and it is healthy. So I already showed you how to do that. Just a refresher. The service runs in a browser. So localhost :9000. Yes. And so navigate to the dashboard that will show you container status and other information. Number 2. So to connect to a Docker container, which is running on the host Pi, from the host Pi. So we know that the container is up and running. Now, how to access it? So we can send it commands using Docker run, or we can open an interactive shell using Docker exec. And Docker exec followed by -IT tells the Docker engine to open an interactive shell. With which container? So that is the container named Mosquito. And where do we get this name from? So again, the Portainer dashboard is our point of reference, is our friend and guide here. And do you see the column name? Yes, so this is very useful because Docker commands recognize these names. They recognize containers by this name. The Docker engine knows which container this name refers to. So it's very convenient to use these names with Docker commands and to refer to Docker containers using these names for when we invoke Docker commands. Yes. So Docker exec -IT opens an interactive shell to Mosquito. So we'll be using this to interact with the Mosquito broker in these steps, in the first step, and then steps 1 through 4. Yes, and What is the trailing \bin \sh? So Docker exec not only opens an interactive shell, it sends this command to that shell, and you can pass additional arguments that that command may expect after this. All right. So since we have invoked the shell without any arguments, we will just get a terminal prompt that we can then use to actually interact with this Linux box inside our Raspberry Pi. Isn't that amazing? Step number 3. Now, to publish to the Mosquito broker running inside the Docker container, we need a Mosquito client. And so we don't need to install the entire Mosquito suite on the host Pi. We don't need it for any other purpose. We only need a client that can publish and perhaps listen to the broker. So it is possible to only install the client. A client-only installation is possible, and do that with the repository on the Pi. So at the terminal prompt, type sudo apt get install mosquito with a ~t - clients. Yes, so this terminal command will install only the client part of Mosquito. There will be no broker. Okay, and so in steps 2 to 4, we will use this client on the host Pi, the same machine that is hosting the Docker containers, as a subscriber and even as a publisher and even a subscriber to the broker. Got it? I hope that makes sense. Yeah. Yeah, so how to publish? So the client needs to publish messages to the broker. So Mosquito has a beautiful syntax. The commands all have a logical flow to them. The command to publish is mosquito_pub, and then it accepts the following parameters. -h tells it the address of the machine where the broker is running. Yes, the broker service. -p, -p. This flag tells it which port that service is listening on. -t tells it which topic to publish to, and -m is the message. And for example, when I want to send namaste, then -m and then in quotes namaste will send this text, will try to publish this text message to the broker on the local host, the same machine where we have opened a terminal and are typing this terminal command, localhost, and on this port. Yes, so this is what these flags -h, -p, -t, -m, this is what they do. Now, if we were connecting from a remote Pi, then localhost will be replaced by the IP address of the machine, and we'll be doing that as well. So we'll get plenty of practice. Now, about the topic, if the topic doesn't exist, then will this raise an error? No. Mosquito is such a wonderful piece of software. If the topic doesn't exist, it will create one for us. And when you see the surveillance/main door, it almost reads like a file path, doesn't it? So it is actually possible to organize topics in this nested fashion, where surveillance is the root topic, and then it has subtopics under it, including one called main door. Yes, and one can publish to any of these topics. All right. The one point of note, though, is that there's no way to list all the topics on a broker. So be wary of proliferation of topics and keeping your topics well organized. Yeah, don't go crazy creating topics on the broker just because one can. Step number 5. So how does a subscriber listen? So there's a typo here. It's a Mosquito sub, not pub. So the command is modeled in the same way as Mosquito pub, except that instead of pub, it is sub. So Mosquito sub I will correct a typo very shortly. -H is the IP address of the broker. -P is the port that the broker is listening on. -T is the topic, and that is it. So this is how we set up a subscriber. We can send text, but how to send an image? So there is a secret in computer science, which is it is all text. It is all text. Even an image is text. And a video is a bunch of images. So even a video is text. And we can encode an image in text using base64 encoding. Yes, so for example, let's say I have an image of Lord Shiva, Mahadev.jpg in my present working directory. Then the command cat Mahadev.jpg will itself return a string version of the image. What does the image look like as text? Yes, but an image is not meant to be seen, to be viewed as text in this way. If we want to view an image properly as text, the appropriate way, the correct way to do that is to encode it in some way. And one way is base64 encoding, which is very common in the world of the web. So we pipe cat mahadev.jpg to base64 command, and this will return the image as a string that we can just ship, for example, using the mosquito pub command. So we'll be doing that a lot. Okay. So the command then, let's look at the mosquito pub command. Earlier we just sent namaste. Now we are sending it an image of Lord Shiva with mosquito pub -H localhost -P 1883 -T surveillance /main door -M. And now we insert the command that I just described into, yes, to stuff the image into, to stash the image into the placeholder for message. And this is the command that we'll use to send image data, right? Now, we will be packaging this image as a payload in JSON format. If you don't know what JSON is, it will be obvious when we start working with it. And to work with JSON on the Pi and on Linux systems in general, where command line is our friend, we have a wonderful utility called JQ, and install it with the sudo apt. So install it from the repository. And that will make working with JSON much easier than typing at the terminal prompt a long JSON string, and in the process is very error prone. So JQ will make this a more robust process for us. Yes, and so we will craft a JSON string containing with complexity, such as containing an image using JQ. Okay, and so we are ready to proceed. Okay, so in step 1, we are going to have a publisher as well as subscriber inside the Docker container where the broker is running, and we will test that out. All right, so let us do step 1. First, I will open an interactive shell to the Docker container Mosquito. So docker exec -it -it. There we go. And then name of the container Mosquito /bin/sh. And here it is. So do you see the terminal prompt? So I'm now inside the Docker container. And First, let us set up a listener, a subscriber to the topic surveillance / main door. So mosquito underscore sub is the command. -h localhost -p, the port is 1883. -t is the topic, surveillance / main door. And that is it. So in this terminal, I now have a listener, and it is listening on port 1883, waiting for messages to come in. So now let us send it a message. Let us give it something to listen to. So I've opened another terminal window. And again, I will get inside the container, docker exec -it, mosquito /bin /sh. And we are inside the container. And now let us publish a message to this topic surveillance / main door. So I'll show you how to do that. I already showed you how to do that. So let's type mosquito pub -h localhost -p 1883 -t surveillance / main door, being careful to type the topic name exactly as we have it, as we have named it. And now the message -m namaste in quotes. So what do you think will happen when I run this command? Let me move these windows one above the other so we can see better. So what do you think will happen? Think about that for a second. And I press enter, and you see the message has just appeared in this terminal window. Okay, let's try it again. Let's type namaste G. And there it is. So the instant I publish the message, the subscriber receives it. Do you see that? Yes. And so this is step number 1, where we opened an interactive shell to the Docker container mosquito. We then set up a subscriber there to the topic surveillance main door. So this subscriber will listen to any incoming messages. And then we opened another terminal window to publish a message. And from this interactive shell in number 3 here, we published a simple text message, namaste, and then namaste G. And the instant we sent the message, almost instantly, yes, it appeared at the subscriber. The subscriber got the message almost immediately. Yeah. Yeah, so that was step number 1. And let's continue this, and let's send the message from the host pie. Yeah. Which means opening up more terminal windows. And this time we will not require an interactive shell. So what I will do is now I will I'll publish a message from the host pie itself. So at the terminal prompt, having already installed a mosquito client, we now type mosquito pub, and again -h localhost -p 1883 -m -t topic surveillance / main door. Checking to see that there aren't any typos there in the name of the topic. And then -m. And what do we want to send? Let us stick with Namaste. And there it is. Do you see that? Yes, so the first two messages were sent from here inside the Docker container, and this latest message was sent from the host machine. Yes, and to show you that we can have any number of publishers and subscribers, let me open another terminal. So lots of terminals, yeah. Open another terminal, and this time I will set up a listener on the host Pi. And again, reminder to have the Mosquito clients only installed on the host Pi, so we can run these Mosquito pub and Mosquito sub commands. This time I will set up a listener. So Mosquito sub, and as before, -h localhost -p 1883 -t surveillance /main door. Yes, and this is our subscriber. So what do you think should happen now? Now, here's the subscriber. It is listening, waiting for incoming messages. And I can send that message from the Docker container, from the interactive shell. And there it is. Do you see? It has appeared in this terminal window where we are listening to it, and it has also appeared in this in the terminal window where we are running the interactive shell. Yes, so in both these places. So here are two subscribers and two publishers listening and publishing to the same topic, surveillance /main door. In fact, let us try publishing from the host this time. Namaste. And there it is. Yes. In both of these terminal windows, the one running the interactive shell and the one that is a terminal window on the host Pi. Yeah. So we will tire of this very quickly. Yes. There's only so much novelty in sending text messages like Namaste and Namaste Ji. Yes, but what we have done so far in the second step, what we have done is we opened a terminal window and on the host Pi, and we published a simple text message to the broker, Mosquito broker, running inside a Docker container. And we opened another terminal window. So now we have 4 of them. And set up a subscriber on the host Pi. And so we set up a system where we have 2 terminal windows, in each of which we published messages to the broker. 1 terminal window for the host Pi, 1 terminal window running the interactive shell, and then we have 2 terminal windows where we have the subscriber. We observe the subscriber in action. Okay, 1 terminal window belonging to the host Pi, and the other one in which we are running the interactive shell. Yes. So, okay, I think that is enough of text messaging. What do you say? Huh? In step 3 now, let's make things a little more exciting, and let us send base64 encoded image. All right. So now in step number 3, let us send an image. Yeah, this is going to be exciting, right? And so in order to do that, let us first explore base64 encoding just a little bit, all right? Just to get the background. And so I'm going to move this terminal window a little, or you know what, I can leave it there. Let me show you the image that I want to send. So in my directory home/pi, actually, let me show this in the file explorer. So in my root directory, I have an image. In my home directory, I have a folder pictures where I have this beautiful image of Lord Shiva that we will ship using MQTT. Okay, so here's the picture. It is reasonably small. It is only 192 by 256 pixels. And first, let us see how to encode an image like this into a string. So using base64 encoding. So what we will do is we will cat this image. So I need to give it the whole path, home /by/ pictures. Yes, there it is. Yes, we'll send it to the base64 utility. So this is available on Linux machines, or at least it is available on Raspbian. If not, install it from the apt repository. So here you see the string that that we converted this image to. Yes, this image mahadev.jpg, and it is a fairly long string. And having converted the image to this string, it is now transportable. We can now use this string. There is no loss of information here. So all the information in that image is contained in this string, and we can encode when sending, and we can decode when receiving. Yes, so at the transmission point, we encode, and at the reception, we decode. Yes, so this is how we can transport images over MQTT, or this is how we can transport images as strings in general. Yes. And now that we have seen how to use base64 encoding, I've shown you how to use base64 encoding to convert a picture, an image, to a string. Now let us send this string over MQTT, and let us observe what happens at both the subscribers. Okay, so we have two subscribers, and from now on I'll just be sending from here, the Raspberry Pi host. Okay, so I could perhaps close this interactive shell, but I'll just leave it open. Yes, so here we go. So again, the command is mosquito pub -h localhost -p 1883 -t surveillance /main door. Got to get that right without any typos. And -m is our message. And so this time, I will be sending my message like so. So in quotes, $, and then open and close parentheses. And then here is where the string will be stashed. And where does the string come from? It's the output, the result of a command. What command? Let's type that in. So cat, we need to give it the path name to the file, the path to the file name with the path. So home by pictures and mahadev.jpg. Pipe this to base64. Yes, so this is the command that I had just shown. And now the string that this command creates will now be published to the broker. So what do you expect this will do? What do you expect will happen? So just take a moment to think about that. Yes. And here it goes. Yeah, and do you see that? Now this base64 encoded image has appeared instantly, in both these terminals. Yes, so both subscribers have received the message immediately, almost immediately. All right. So this is step number 3. What did we just do? Well, first we saw how to encode an image into base64 string, how to convert an image to a base64 encoded string. Yeah. First, we saw how to do that at the command line. Command line is our friend. And then we used that. We went one step further and used what we just learned to publish the image to the MQTT broker. Yes. And of course, it is base64 encoded. Yes. So it appears like a string. So to actually recover the image, as we saw in the folder, right? To recover the image as we saw it here, we need to decode it. Yes, and so that is something we haven't done, and that is something that doesn't belong at the subscriber. Yes, yes, but we were successfully able to send the image. As we progress, we will also not just receive the image at the subscriber, but once we wade into the world of Node-RED, we will decode the image also and recover the image as we saw earlier. Yes. So congratulations. You have just learned how to use MQTT to send messages, including images, across. So in the next step, we will see how to bundle this into a JSON payload to send over MQTT. So we will still be sending an image along with other information. So in the real life scenario, the image will be traveling with other information. So for example, when a surveillance unit detects motion or detects intrusion, it will raise an alert. And so this message will travel together with the image. And how do we do that? We package all the information together using the JSON format. So the base64 encoded image, which is a string, will travel with other strings with information like alerts, etc., in one JSON payload. So in the next step, we'll create one such JSON payload and send it across. Okay, and so in step number 5, I believe, step number 4, yes, step number 4, in order to send the base64 encoded image as part of a JSON payload, I will need to create a variable to hold this base64 encoded image, this string, yes, this very large, this large string. So I'm not going to type the commands now. I'm just going to go back to where I've done it before. So what I'm doing here is I've created a variable, yes, a bash variable. So bash is the shell, the bash variable b64, which now holds the string, yes. So instead of creating that base64 encoded image, that string, and sending it immediately via Mosquito Pub, I'm holding that string in a variable. So let us see what is in the variable and satisfy ourselves. Echo in quotes $b64, $b64. That's how it is. Is that how it is? Yes, that is how we see what's in the variable. And yes, we see that the base64 string is in the variable. Let me clear up some space here. All right. And now with this variable, I will create a JSON payload with this and some other information. So I will do this using the JQ utility. And again, you should have it installed. If not, follow the instructions that we discussed earlier to install JQ from the apt repository. And so what I've done here is JQ just gives a way of creating JSON, creating a JSON payload, which is more robust than typing the entire JSON string at the command prompt. So I've created the JSON payload and I have stashed it into a string, a variable payload, or all capitals, yes. And JQ accepts arguments. So the argument from has the string host by, all caps. Message is where I'm stashing the image, the base64 encoded image. And then subject is another string, mockup for test, all caps. Yes. And from these three variables, these three arguments to JQ, from, message, subject, I'm crafting a JSON payload. This is again a string, so it is quoted, and in curly braces, the key message holds what's in the argument message. So that is the base64 encoded image. The key from holds what's passed as the argument from, and the key subject holds what's passed as the argument subject, arguments to JQ. So the JSON payload has three keys, message, from, and subject. And message is the one that is holding the base 64 encoded image. So this gives us the payload. Yes. And now I publish mosquito pub -h localhost -p1883 -t surveillance /main door -m. And now what I have is the payload, right? So now what do you think this will do? Yes. So just before I fire off that command, here is what we have showing in the terminals, in the two terminals, one for each subscriber. What do you think will show up here? And so away we go, and there we go. Now both of these subscribers have almost immediately received the JSON payload. And how do you tell it is JSON? You see the keys from, subject, yes. And if we scroll up, this is a long string, so we may not be able to scroll all the way up. Let us see if we can do that. Yes, there it is. So here is the curly brace that marks the start of the JSON payload. And then as we scroll, yes, it has the key message followed by colon, and then the base 64 encoded string. And this string, let us see, let us find the end of the string. There it is. Yes, in this key value pair message, and then the base 64 encoded image is followed by these two other key value pairs from, host pi, all caps, and subject, mockup for test, exactly what we had in the payload here that we created here. Okay. Yes, so we are able to send a JSON payload from the publisher to the subscriber. And what did we just do? Yes, here we are. So still on the host pi, we saved the base 64 encoded image as a variable. And then we stuffed that variable, we stashed it into a JSON payload along with other key value pairs, other pieces of information, a message and a sender, and a subject. And then using the by now familiar mosquito pub command, we sent this JSON payload. This JSON payload is a string which is stored in a bash variable, payload all caps. And so we use that with mosquito pub to send that entire payload over to the broker. Yes. And so we are able to send messages. What have we achieved so far? Yes, we are able to send messages, text messages, images. Yes. We are using the MQTT protocol. Same so the last little bit, so in the next 3 steps, we'll be sending a text image, a base 64 encoded image, and then a JSON payload from a remote Pi. But before we go there, you must be wondering, how do we recover the image from these base 64 encoded strings? Are these even images? So before we move on, I'll let you in on a little secret. I have implemented Node-RED workflows where we can preview the image when a JSON payload is published to the topic surveillance /main door, and also see these images in a dashboard, view these images in a dashboard. So let me give you a sneak preview. Let me move some of these terminal windows so we can see the web browser. Let me move these out of the way. And here is Node-RED running in the web browser. This workflow that I've implemented gives a preview of the image. It has a node, which is a subscriber to the topic surveillance/main door on the MQTT broker. And other nodes that convert the payload to a JSON object and then decode the base64 encoded image and show it in the preview window. I also have other Node-RED workflows that take this image and display them and display the image in a surveillance, display the image in a image gallery for viewing. You can see the images of Lord Shiva that we published to the broker appearing here in the Node-RED dashboard. The actual Node-RED workflows, the actual Node-RED flows, and the details of their implementation, I will cover in a different video. For now, know that the Node-RED flows accept the base64 encoded string that is part of the JSON payload and enable us to preview it as well as view it in the image gallery. So with that, I'm going to close some of these terminal windows. We have too many of these open. The only ones I will retain are the ones that have the listeners. This is a listener. And I'll just stack these on top of each other. Okay, that should be good. And now what we'll do is, in a similar way, I have this terminal, this real VNC terminal to connect to the Raspberry Pi hosting the MQTT broker. We will open another, we'll use real VNC to open another terminal to the Raspberry Pi surveillance unit. And from there, we will use the command line interface to send a text message, a base64 encoded image, and a JSON payload to the MQTT broker. So now I have this real VNC terminal open to access the surveillance unit. I have opened a terminal on the surveillance unit, and the Mosquito client is already installed. So let's start by sending a text message to the MQTT broker. We do that with MQTT pub -h. So this time, since this Raspberry Pi is a remote Pi, I need to specify the IP address of the machine where the broker is hosted. That is 192.168.1.254 on my local network. Port is still 1883. Topic is still surveillance main door. -m message, namaste. And what do you think will happen now? Namaste from remote Pi. Okay. What do you think this will do? Let's send it. And now let's go to the Pi hosting the MQTT broker. And here is the message, Namaste from remote Pi. So step number 5 is complete. And we have, what have we achieved? So we opened a terminal window on the remote Pi this time and passing the IP address of the machine hosting the MQTT broker, we were successful sending a text message. So step number 5, with that, we have completed step number 5. In step number 6, we will take one step further and send an image. And this time, we will send the image of a flower, a different image from the image of Shiva that we were using before. We will send the image of a flower, or at least I think it is a flower. And this will, we will also go to Node-RED and see does the flower really appear in the preview as well as the image gallery there in the Node-RED dashboard, the gallery in the Node-RED dashboard. All right. So back to the Pi, and the image is in the pictures folder. And it is this flower.jpg. Okay. Again, it's a 474 by 475 pixels image, a little larger than the image of Mahadev Shiva that we were using before. And I've picked a different image intentionally to show the difference when this image appears in the preview in Node-RED as well as in the image gallery. Yes. So I'm going to close this, and now I'm going to go back to the terminal window. /home/pi/picture. Flower.jpg. Pipe to base 64. And we need the $sign. And what do you think this will do? So think about all the places where this message will appear and how it will appear. All right, so let's send it on. And first of all, it appears to have made it in both these terminals. However, the image of Shiva has not updated in Node-RED. Why? Because the Node-RED flow expects a JSON payload. And if we scroll down here in the debug window of Node-RED, we will look at Node-RED in more detail in another video. If we look at the debug window, which is this pane on the right here, then there is an error message there, which indicates some problem with the JSON payload. Why? because we haven't sent a JSON payload. We have sent the base64 encoded image as is. Let's fix that in the next step. Yes, and have the base64 encoded image appear not only in these terminal windows as string, as the base64 encoded image, the string, we also have the preview updated in the Node-RED flow and in the Node-RED dashboard. Yes, in the Node-RED dashboard here. Okay. Okay, so first I will create a variable, a bash variable, b64, that has the base64 encoded string for the image of the flower.jpg. We'll echo to make sure that the variable is set up as expected. Yes, there it is. We'll clear the terminal. Next, we will stash this base64 encoded image into a JSON payload. Now this time, in the from the sender, I have the remote pi, the string remote pi all caps. Well, previously we had host pi. So when we see this image in the terminals, the subscribers, when they receive this image, we will be able to tell this image, differentiate it from the image that we had sent earlier. Okay, so that's the payload. Let's echo to make sure that it is what we expect. Yes, there it is. And you see the key from has remote pi. And now let's clear up the terminal. And now let's publish this payload to the MQTT broker topic surveillance / main door. So I'll pull up the command from before. And stash the JSON payload in the slot for message. And now, before we send it on its merry way, before we send a payload onward, what do you think will happen? Yes, so there it goes. Now let's go back to the pi, and we see the image of the flower in the preview. Let's go to the image gallery, and we see it there as well. So the latest image has come in. And when we look at the two terminal windows, we see that this payload has arrived. And how do we know that that was indeed the payload that we sent from the remote pi? So now you see why we have these key value pairs from and subject. So the from says remote pi in both of these windows. So our scheme is successful in sending text, image, and JSON payloads from a remote pi to the MQTT broker. Yes, so this was step number 7, our last step in this experiment. And what have we achieved here? We sent the base64 encoded image using the mosquito pub command at the terminal prompt from a remote pi. And we sent text, we sent the image as a base64 encoded string, and then we sent it as a JSON payload, as part of a JSON payload. So this completes our demonstration. And there is one one more item that I want to cover, which is automation with Python. So I will show you how to automate this process that we have been executing using the command line interface with a Python script. And then we will start with the basic Python script, a simple Python script, and then we will expand upon it in a subsequent video to add features like motion detection with image analysis and object detection with deep learning. In the next video, we will also look more closely at the Node-RED workflows and understand how they are implemented step by step. So we've seen how to use MQTT in IoT apps from the command line interface. So that is manual process by hand. Now I'll show you how to automate the process in Python. So we'll send images in a JSON payload. We'll send an image in a JSON payload over MQTT at regular intervals from the surveillance unit to the broker. And here is my script in the GitHub repository surveiller. Import the PAHO MQTT client. And this client works in an event-driven pattern. So what is the event-driven pattern? In the event-driven programming style, we implement event handlers. And what is an event handler? An event handler has two parts, an event and a callback. So the event triggers the code in the callback to run. So this PAHO MQTT client supports 7 events. Connect, disconnect when the client connects or disconnects from the broker. Subscribe, unsubscribe when the client subscribes or unsubscribes to a topic on the broker. An event for publish when the client publishes a message, and an event for when the client receives a message. This would be a message published to a topic that the client has subscribed to on the broker. And then an event related to logging. So each of these events has an associated callback, and the callback is a Python function. I have used the same name for the Python function as the name of the event. So what happens in the callback is print statements. So for example, the onPublish, the callback of the onPublish event will publish the message ID. Note that each callback function must accept the client as the first argument. Also note that to start listening to events, we call the loop start method of the client. Usually right after the client has connected to the broker with the broker's IP address. This creates an interesting conundrum. There are 2 forever while loops running in the same program. One loop is listening for events. So the moment an event occurs, it can trigger the callback. The callback is triggered. The second loop is taking a picture, packing it into a JSON payload, and then publishing it to the MQTT broker at a regular time interval, every delta seconds. So we have 2 forever while loops in the same program running simultaneously. How is that possible? What gives? Okay, so this is possible because the PAHO MQTT client library will launch this forever while loop where the listener in its own thread. So it is isolated from this forever while loop in our code that takes a picture, packs it into the JSON payload, and publishes it to the topic surveillance/main door on the broker every delta seconds. This is a very interesting feature of the PAHO MQTT client library used in this program. And so now we will run this program on the surveillance unit. So from the terminal, Python 3 sentry.py is the name of the program, and it has kicked off. And what do you think we should be seeing now? So let's go back to our broker. What do you think we should be seeing? So every delta seconds, and I've set delta to 30 seconds, what should be happening here? Well, we will receive the JSON payload from this surveillance unit, and that will appear here. And in Node-RED, we should be able to see the image update. So here's the latest payload, and Node-RED has updated. Yes, so you see in the image preview, we now see the surveillance unit has sent a picture of the entrance that is being surveilled, and the image gallery has also been updated. And every 30 seconds, a new picture will come in with a timestamp, and the image gallery will show the latest 3 images at any time. So it will keep getting updated. So this image has just come in at 5:58:30 in the morning. So it's almost 6 a.m. in the morning here in St. Louis on 12th of December. We'll give it another 30 seconds. We are now viewing the Node-RED dashboard. And as the third image comes in, yes, its timestamp is 559:0, so 30 seconds after the previous one. So every 30 seconds, a new image is coming in. Last in, first out. And so that's how the image gallery is continuously updated. These are the Node-RED workflows that are listening to the topic surveillance/main door with a subscriber node, and then processing the image to convert the JSON payload as a string into a JSON object, update the image gallery, and plug the image into an HTML template for viewing in the dashboard. All of these details we'll look at in another video. This concludes today's presentation. We started by installing Docker and Docker Compose and the IoT stack on the Raspberry Pi. Then I showed you how to use the MQTT protocol to send messages, text, images, JSON among devices networked in the Internet of Things. Then we automated the process in Python, taking a little help from Node-RED for viewing images. So this is the basis. This is the basic framework of my surveillance system, and it can be expanded in an infinite variety of ways. A Raspberry Pi, one can add sensors to the Raspberry Pi and also control appliances with it. So what we have here is a system, for a home automation application based on networking Raspberry Pis and perhaps also other microcontrollers like the Arduino or the ESP32 for home automation. So in the next video, I will build up on the Python script to add smarts to it for motion detection and intrusion detection, and also dive deeper into the Node-RED workflows. Thank you.